You're all set, Diganta. I made you co-host, and we are ready to start. Two people that promised have shown up. Week said that he'll show up as well. So, but we should start. He was there in the afternoon. I also have Arpan Kar. No, not Arpan Kar. What am I saying? Huh? Ankit Kar. Okay. And well, we'll talk about that. I mean, he wants to present some stuff. We had assigned. No, we'll talk about that. So you can go ahead. Yeah, you're all set.
Yeah, sorry, I didn't realize I was on mute. Yeah, can you hear me?
Diganta.
Hello. Hello. Hello.
Diganta.
Hello. Can you hear me?
Yeah, but volume கொஞ்சம் ஜாஸ்தி பண்ணுங்க. ஓ எனதுலயே volume கொடுத்து. இல்ல கேக்குறது.
Hello. Hello, is this better or is this
Diganta, you're not coming through. I can hear you very faintly.
Is this better? Hello. Is this better? Hello. Is this any better? Hello. Hello.
Just one moment. There is some technical issue here that even Shankar cannot figure out.
Is it possibly on my end? Can you hear me now? Hello. Hello.
Now you're better. And the volume just. Now speak up, Diganta.
Hello. Can you hear me now?
Yeah. So you're good. Good to go. Okay. Thank you.
Yeah. So let me share screen once more.
Yes, please.
Okay, sure. So is this visible?
Yeah, you can go ahead.
Okay. Yeah. So last time I was basically talking about this about some background for this LP duality. So we decided that it's good if I give some short introduction to this. So that is sort of what I will begin with. So firstly, consider this particular LP problem where, you're trying to minimize this f, where f is some c times x. So c and x are both vectors here. And we have some constraints. So in LP, all of our constraints are linear. And of course, all of our variables are also going to be positive. So we are assuming that our variables are positive. All of this generalizes to the case where they're not positive as well, or where, this equality is turned in the opposite direction. But I'm just presenting this particular case for presentation for clarity's sake. Right. So then this problem is called the primal problem. And, the minimal f, we're just going to call it f star. Right. So to get to the dual LP, or to get to the understanding this concept of duality, the question we ask is, can we find a lower bound for f star in an easy way, right? And it turns out that that is possible. So what you do is you take these constraints and you multiply them with some positive coefficients yi, and you take some linear combination, right? So we're going to take some linear combination of the constraints that we began with, right? So when you take linear combinations, it's like you're deriving a new set of constraints. You're learning some new clause from the existing clause. So if you have some, x naught plus 2x1 blah 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 is less than equal to 5, and x1 plus 3x2 is less than equal to 6, you can actually, from both of these, derive a new constraint that says something like 2x naught plus 4x1 plus 3x1 plus 9x2 is less than equal to 10 plus 18, right? So I've taken this times 3 and this times 2 and just added them together, right? So as long as these guys are positive, I can always do this. This is always something sound that one can do in linear arithmetic, right? So you can always take some positive coefficients yi and multiply both sides by that and take linear combinations to get new constraints of this form, right? Now, suppose also you've chosen yi so that this condition holds, right? Where what are we saying? Where this combination of these coefficients in this new constraint that we have, the coefficients is new constraint, they are actually less than this objective c that we have, right? Then this actually allows us to derive a lower bound for this f. Why? Because now that we have this, we can then substitute this into here to get that f is going to be greater than equal to this, right? So if you multiply both sides by x here, and remember that x is also positive, so you can do that, then what you would get is you get f on this side, and you get back this on over here. So you get an inequality that looks like this. And then, of course, from here, what you get is this. So what you get at the end is that this expression turns out to be a lower bound for f. And in fact, this is true for all possible values of x, because this chain of inequalities holds for all x. So then this expression becomes a lower bound for f star, right? So notice that we have just constructed a new LP, right? What are we saying? We are going to, okay, so we're not going to maximize G. This is a mistake.
What is y here?
So why are these coefficients that we are taking linear combination of these existing constraints by? So what we're doing is we're basically taking,
Why you could choose.
yeah, why we can choose. And it
Combination.
turns out the kind of values of y that will give me a lower bound itself are, form an LP. So that is called the dual LP. So consider this LP.
Choose y carefully, otherwise your lower bounds will be too.
Yeah, it will be too loose. Right. So let's look at what is exactly that we need to do to choose y, right? So remember that y are these variables, right? So now suppose consider this LP where what are we saying? We're not going to say c times x, this is an error, but we are going to say that, we're going to try and maximize this expression, sum over yi bi. So this expression that we had over here, right? And remember that this expression was the lower bound for s star. So we're going to try maximize this, and as constraints on yi, we are going to put in these constraints. Remember that these are the constraints that we needed to make sure that this expression was the lower bound of f star. So we put these as the constraints for yi, and of course we also make sure that y is greater than equal to 0, right? So then what do we get? We get some linear objective and a bunch of linear constraints. This is precisely what are the things we need y to satisfy, so that this expression becomes a lower bound. These are precisely those constraints. So when we say that we need to choose y carefully, what do we need to do? We precisely need to choose y so that these constraints hold, and so that this expression is as large as possible, because this expression is the lower bound. We want a lower bound that is as large as possible, right? So essentially, to choose y, we need to solve this LP problem given by this objective and these constraints. And when we solve this problem, let's say that we get some optimal G, call it G star. What we have is this lower bound where we are saying that G star is this optimal value is always going to be less than equal to the optimal value of this original LPF star, right? So this is the dual LP problem. Now, a few interesting properties of dual, which I'll just mention without proof. It's not particularly difficult to see, but the first is that the dual of a dual is basically the primal. So if you start with any LP, you can take a dual, and then on that dual you take a dual again. What you'll get back is exactly the same LP that you started with, right? So this is indeed like a strong dual kind of a situation where the dual of a dual is the original thing that you started with. And that immediately gives us that the optimal value that you get from solving the dual. Yeah.
I have one question here.
Right.
Okay, maybe this is too basic question. See, usually LP, even with an objective function,
Right.
is it stated in the way that you have stated here to solve for coefficients? I know that
No. So
you
the
know the
original
coefficient
LP.
but you have fixed the coefficient. No, but you're maximizing G. That's all. You for a fixed coefficient of Y. Y is still you have chosen it. You're not solving for Y.
Right. So basically, this is what's going on. So we have an original LP where what do we have to do? We have to solve for some variables x, right? But instead, we can take coefficients y, and if y satisfies this set of constraints C bar, so this LP is what? Some objective F and some set of constraints C, right? So if y satisfies set of constraints C bar, then that means that this y basically give an upper bound for. So if it satisfies C bar, then this new expression G is an upper bound, or sorry, I mean a lower bound for F, right? So if y satisfies this C bar, then this expression G that we have over here is lower bound for F. Right? So we started with an LP which is F and C, where the idea was to solve for X. But then we said that, okay, let's take coefficients Y. And then we found this condition on Y where, if Y satisfies these conditions C bar, then we can say that this expression G is a lower bound for F, right?
But why is this problem simpler and a simpler LP problem than the previous one?
It in some cases might be, and we will exploit this problem to prove completeness when it comes to Betacrown and so on. So this will be sort of the path of the. So I'll not give the full details of the proof, but at least for intuition's sake, this will be sort of the path of how we would come to that conclusion for Betacrown, right? And so this is basically the dual problem. So the dual problem is just this C bar and G.
So why do you
Yeah.
want to find the lower bound for F star?
Yeah. So
it's a good question. So because you want to solve the LP with, if you go up, you want to solve the constraint. But I thought the constraint was like a you somehow posed it as maximize something, but that was not your original problem that we started with when you introduced constraints in the crown thing, no? So those constraints required you to maximize something. So that's, I think, related to Avik's question of why do you want to compute the lower bound? I mean, I know if since you're trying to maximize that LB, even if you don't find it, some lower bound will be some some solution which may not be the most optimal solution. Correct?
Yeah. So there's two answers to this question. So one is, of course, at least I'm looking at your question from two parts. One is, of course, how is an LP stated like this, even related to the neural network verification problem, because here I'm saying minimize F, whereas there is no minimization going on, and we'll come to that. There is a way in which you can view neural network verification so that it becomes sort of a minimization problem, quote unquote. The other is, why even take a dual? Even if I'm given an LP where I want to somehow.
But if you remember, if you recall, last time when you left off,
Yeah.
the reason this constraint came into picture inside the LP was because you wanted to solve the gradient descent, okay, under certain constraint, correct? So I thought, is this related to solving that?
Yes. I mean, I will relate it back to that. Yeah.
Okay. So
So
here,
this is just sort of a detour for background sake.
okay.
Yeah.
So I wouldn't take it, that way. Yeah. So hopefully you will relate it. Okay. Yeah.
Yeah, I will relate. I think in some later slides the connection to this concept of duality will become clear. I just want to make it very clear here, just so that when we see it in the context of this alpha beta crown, some of these dual constructions are clear, right? So this is just a sort of separate detour that I'm taking in this slide, just to give this background of what duality is in the LP context. So, and that is just to construct this dual problem C prime G from the given primal problem FC, and understand that solving the dual and solving the primal is in some sense equivalent. So if it does turn out, which in our case it will turn out, the dual problem looks somewhat nicer, then basically we can go from the primal to the dual, solve it there and come back and so on, right? And the connection between the primal and dual is via taking these coefficients and taking linear combinations of constraints, right? So yeah, I just wanted to give that sort of a background to this, primal and dual view, because a few times in later slides we'll go from primal to dual and dual to primal and so on. Okay, so I understand if this is, if the motivation for why doing this is not clear, then just bear with me. But what we are doing, if there is any question about why, what this dual is, or why is it the case that this is giving me an lower bound and so on, then are there any questions like that? If not, then I'll go on to the next slides and the why will become more clear there. Okay, sure. So I'll move on.
Yeah.
Okay, so now we come to this.
Today you have to time your problem. I know because of technical issues we started late, but 6 you have to end, okay? Because the
last shuttle, yeah.
Yeah.
Sure. So I'll go as quick as I can. So firstly, there's this duality view of crown, right? So crown, remember that this was just some bound propagation thing, right? But what we can do is we can actually look at it as solving some sort of an LP problem, and then look at what it looks like, take the dual of that and understand what is going on from that perspective, because this is the perspective from which alpha crown and beta crown makes most sense, which is this LP dual perspective, right? So remember that what did we have? We had some neural network, right? So let's take some neural network, some 1 1 minus 1 minus 1, and let me draw out whatever the ReLU constraints as well. Right, and what does crown do? It essentially, so for each one of my variables, it'll essentially do this sort of a thing, right? Where it has some bounds of x4 in terms of x2, right? So it will say that x4 is less than or equal to x2, greater than or equal to, maybe less than or equal to x2 and greater than or equal to some x2 plus 1 by 2 or something like that, right? Depending upon the bounds that we get for the interval bounds and so on, right? So we had some constraints of this form, and similarly x5 is again less than or equal to x3 minus x4 and greater than or equal to the same thing, x3 minus x4 and so on, right? So when we are propagating bounds with crown, what do we really have is we have some bounds on this variable, on each variable, in terms of the inputs to that variable, or to whatever value is being computed at that variable, right? So we have bounds on x4 in terms of x2, on x5 in terms of x4 and x3, and similarly on x1 in terms of, x naught and so on, right? So we have all of these bounds. So we have a bunch of collection of these bounds, and this itself forms some LP constraints, right? And remember, what we want at the end is we want an upper bound and lower bound for the output, right? We want to propagate bounds across the network. So what we want is a lower bound and upper bound for the output, right? So for now, let's just not worry about the upper bound. So, the upper bound case is going to be symmetrical, but let's look at the lower bound case. So what we really want is we want the lowest possible value of this output variable x5, right? And this again is an LP objective, correct? So whatever Crown is doing in this bound propagation can be thought of in terms of solving this particular LP problem, where the constraints are given by this kind of relations between this variable and so on, as we have seen before. And the objective is just, minimize the output of the network, right? So given that, this is the linear relaxation of the network, here is, some approximation of ReLU, here is what the weights and biases are doing. Given that we have linear constraints approximating all of that, over approximating all of that, what is the smallest value that the X5 can take, right?
It's his end, I think. Diganta, there is on the right corner.
Oh, this one?
Oh, maybe it's me.
No. Okay, I'll just remove this. I don't know how to.
I think once he starts talking, it pops up. Okay. So maybe
I'll just push it as far into the corner as I can. So this is something that Zoom has, which I don't know what I can do about. Yeah, it's not hiding anything important that I'll make sure of. Is this gone now?
It is kind of reduced, but yeah, go ahead. Yes, let's not waste time.
Yeah. So sorry about that. So if it is
really blocking
something. Yeah. Okay. So this is the idea, right? So there is an LP optimization actually implicitly going on inside Crown, right? So the Crown paper itself doesn't talk about it in those terms, but you can sort of think about whatever Crown is doing is it's trying to solve this particular LP problem, right? Where your constraints are all of these, ReLU linear upper and lower bounds, the linear upper and lower bounds coming from the weights and biases in each layer. And the objective is that you just want to find the lowest possible or largest possible symmetrically value at the output of the network, or for each output of the network, let's say, right? So it's trying to really solve some of these LP problems. It's trying to really solve an LP problem in some sense, right? So then in that sense, we can say that Crown solves this LP problem, right? But no, so Crown doesn't really have to call something like a simplex solver, like a full-fledged LP solver to call this problem, right? To solve this problem, right? It is actually able to solve it in a much faster way via back substitution, correct? So what is back substitution going to do? It's going to take each one of these constraints. So it's going to take this constraint and or let's say this constraint and then substitute it into this particular constraint, right? So it's going to take each one of these constraints and sort of substitute it into the constraints involved in the other variables, and then substitute that into other constraints and so on. And if you keep doing the substitution, eventually what you have is you have some bounds of x5 in terms of x0, and then you can substitute the bounds of x0 and you get some lower and upper bounds of x5, right? So it turns out that this particular LP can be, the way it's designed, the way the Crown's domain is designed, that the LP that we get here can be very easily solved via this back substitution method, right? So you don't need a simplex solver for that. So, okay, that's fine. So then the question is, what happens in the dual view? What happens if we try to take the dual of this LP? Any question?
No.
Okay. So what happens if we try to take the dual of the LP? Remember that solving an LP is exactly the, if you want to solve the LP, that is, if you want the optimum value of the objective, right? So in this case, when we are saying solving, what we're really looking for is the lowest value of x5.
Diganta, I have one question here. So back substitution, you're doing mainly to express all these inequalities on the left side in terms of the inputs, right?
In terms of the inputs, yeah.
But you still have to solve the LP problem, correct?
No, we don't have to solve the LP problem, because once it's
get the lowest bound.
No, we don't, because once it's this back substitution itself is actually taking care of solving the LP problem, because once it's in terms of the input, what it will look like is something like this, where we'll say that, this x5 is less than equal to some, some 5. I'm just putting some random values here, 5x0 plus 4 is less than equal to some x5 or something like that, right? So once we have this, and then we also know that x naught itself is, let's say, between -1 and 1. And so then we can substitute this over here and say that, okay, then, x5 is less than equal to 4 minus 5. And we get x5 is greater than equal to -1. And
But this is no better than what deep poly does.
yeah, exactly. I'm not saying it's any better than what deep poly does.
Oh, but
I'm
I
saying
thought
what
the
deep
Crown was doing something better to get
Mm,
top bounds, and that's why we're all these constraints solving was the issue. So if this is just not doing anything better than deep poly, then what is okay?
No, yeah, I've not come to alpha beta crown here. There is still no alpha or beta in this picture right now. So I'll come to that. But what I'm talking about is right now just deep poly. So all I'm saying is that whatever deep poly was doing, it can be viewed from a point of view of solving a particular LP problem in a smart way, right? So you could have made an LP call, but the deep poly says that you don't need to. You can just do this back substitution and solve the LP, right? So the LP problem arising from the constraints that we have in this sort of a neural network verification problem, this LP problem can be solved easily via back substitution. Yeah.
So you say the whole network can be encoded into an LP problem.
Mhm.
But so when you're creating these constraints, in that you need to partially solve the LP problems, right? Because you need to find intermediate LBs and UBs.
Yes, that's a very good point. So that's a very good point. So essentially, there's not one LP problem here. If you really think about it, so this is sort of the backward view of things. If you really think about it, we are actually, so each time we're taking an LB and a UB, we have to solve one LP problem for that as well, right? So essentially, there are as many LP problems here as there are nodes in my network. And if that sounds very inefficient, don't worry, we're not actually going to do that in the implementation. There's no LP calls going on. So does that answer your question?
Yeah.
Yeah. So yeah, so there are more than one LP problem. So right now I'm just ignoring I'm just assuming that these intermediate LVs and UBs are fixed. But yeah, to fix those LVs, you'll need to solve individual LP problems as well. And that is, I mean, yeah, kind of we'll come to that. It is a point that I will come back to later on. Yeah. Okay, so we are on the same page that whatever crown or deep poly without the alphas and betas, whatever it's doing is just that it has figured out a nice way of solving this particular LP problem that you get, right? If you fix the LVs and UVs if you fix the intermediate concrete bounds at each neuron, right? Okay. So then what is the dual view of this LP, right? So we can solve this problem easily. But what happens if we take the dual point of view for this? So really the way that we're solving is doing some back substitution, right? But then doing this back substitution can be thought of as taking linear combinations where the coefficients are taken to be 1, right? So if I'm substituting this inequality into this inequality, it's as if I'm taking 1 times this inequality and adding it to 1 times this inequality, right? So whenever we're doing this sort of back substitution, what we're essentially doing is taking a linear combination, but the coefficients are all 1, right? So from a dual point of view, what crown or deep poly is doing, all that it's doing is solving the dual LP by just setting correct coefficients to 1. So it turns out again that the kind of LP you get here can be directly solved by setting the coefficients greedily or smartly to 1, right? And this gives directly a solution to the LP. So this is the point of this slide, that crown can be viewed as a quick way of solving the dual LP. And how does it do that? It does that by setting the coefficients to 1, right? Okay.
But it's only 1 in this example, right? So for example, if the weight was something different, suppose
Yeah.
it was x3 minus 3x4,
Right.
then you couldn't just set it to 1 because you'd have x2 less than equal to x4. And
No,
then you'd have,
even then the coefficients would still be 1. So let's take that example, right? So let's say that you have some situation where I have got some so this guy, let's say that this is x3, x1, x2, and I'm saying that I've got already some bounds on x3. So I'm saying x3 is Sorry. So I'm saying that, we have some whatever expression, let's say gamma is a lower bound for x3, right? And then what do we have? You're saying the weights are 2 and -3, right? So what will my coefficients, constraints with respect to that look like? It will look like something like this, right? The x3 itself again is less than or equal to x2 minus 3x1, right?
Yeah,
So then
correct.
when we do the substitution, what we're essentially doing is we are saying that, okay, gamma minus x3 is less than or equal to 0, and x3 minus x2 plus minus 3x, sorry, minus x2 plus 3x1 is less than or equal to 0. So let's take now 1 times this plus 1 times this, and then we end up with this sort of an equation where we're saying gamma minus x2 plus 3x1 is less than or equal to 0, right? So whenever we're doing this substitution, this is what this basically looks like, right? It's equivalent to taking this sort of a linear combination. And the coefficients will turn out to be 1. The only way it would be something else other than 1 is if before doing the substitutions, you would have multiplying both sides by some other factor, which we're not doing anywhere inside crown or deep poly, right? So does this answer your question?
Not really, but I think it can wait for later. I'll come back to it if it continues to be a problem.
Yeah, sure. And yeah, I mean, we can also connect offline given the time constraints, I guess. So feel free to mail. So okay, so yeah, so this is the sort of situation, right? And of course, all of the coefficients won't just be 1. There will be some coefficients which will also be 0 because the substitution, which constraints to substitute in depends on whether the sign of the weights is positive or negative or not, right? So there is that detail there, but for the sake of time, I'm not going to be able to go into an example demonstrating that, unfortunately. But we can connect offline if you want more details.
So at the end of this thing of back substitution,
Right.
what do you get? I mean, you get the precondition, huh?
Yeah, we get basically a single set of constraints relating the the input variables and output variables, right? So if you start out with some concrete bounds on the output variables, then you would get some weak precondition. Or if you then
It's not, is it a weakest I mean,
it is not a weakest. It is not weakest because we are over approximating.
Yeah, it's an under approximation of
it is, yeah, everything is still an over approximation. We are over approximating value, so everything is still an over approximation, right?
It's an
So this
over approximation of the weakest precondition.
no. I mean over approximation in the behavior sense. I was saying it will be an under. It will not be the weakest precondition. Yeah, it will be an under approximation.
It will be too stringent, not.
Yeah. Right. Yeah. So if we started with some bounds on the output, we would get something that is too stringent for the input.
Yeah, that's because, like you said, in the dual LP problem, that's only the lower bound. Okay, correct?
Yeah, and the point here is that this LP problem itself is an over approximation. This LP formulation itself is imprecise. This is itself imprecise, right? Because we are over approximating ReLU, or let's say over approximating ReLU. So even if we solve this LP precisely, the output, the bound that we still get, depends on what you solve for. You can solve for the input to get some precondition, or for the output variable to get some post condition. But whichever one you do, it will still be imprecise because the LP itself is imprecise. Right? So a neural network can't be precisely represented by an LP, which is why it is an over approximation. And the precise over approximation where it comes in is when we're handling ReLU by doing that linear upper and lower bound, that triangle bounds, and so on. Is this okay?
Yeah.
Okay, sure. Okay, so this is LP and the duality view of crown. So now we come to the first of two pieces of alpha beta crown. There's two pieces behind it, which is alpha crown and beta crown. So let's talk about alpha crown. Yeah, so somebody, I think in last to last class pointed out an issue I don't remember how many classes back it was at this point, but like I think somebody pointed out an issue where when we're choosing this sort of lower bound, we have these two choices. We can either choose this line and take triangle 1, or choose this line and then take triangle 2, right? And somebody pointed out that, okay, even in the case where these two choices are locally equivalent, so let's say that the intervals are this and this, right? So even in the case where they're local equivalent, it might still, one of these two might still give me better lower bound. That in fact, choosing to take triangle 2 will give me a better lower bound compared to choosing to take triangle 1, right? So, and that was a very good point. So in fact, this choice, making this local choice of between these two lines, it is actually something that can affect the quality of the bounds in very non-trivial and hard to track ways, right? So something might look like, triangle 1 might be smaller than 2, but still if you choose triangle 1, it might turn out that later on you are somehow paying more penalty because of the non-linearities involved in the later layers than what you would have paid if you had chosen triangle 2, right? The entire network is non-linear, so it's not really clear between choosing 1 and 2 whether which of them will actually give me a better bound finally in the output side of things, because the entire network is non-linear, right? So this can affect the quality of the bounds in subsequent layers. And it can affect the intermediate bounds as well, as somebody pointed out. So, what can we do, right? Can we do something better? So there is something better that has been tried in a different domain, which is in this LP relaxation domain, where what people have tried is basically they say take both, right? So what we do is take both. So then the over approximation ends up looking something like this. You have this, and then you have this. So this is called the triangle approximation, right? So there, if again, from the point of view of trying to approximate the network as with a bunch of LP constraints, this works, right? You can say that, okay, my value of the output of ReLU is going to be below this line and above both of these lines, right? So this actually works. And there is a paper called Planet, which when it came out, had good results with respect to this sort of a method where it will use both the possible lower bounds and therefore get something even tight, right? So here you actually end up avoiding both this region 1 and region 2, correct? But there, you see, now you can't avoid making an LP call, right? So now you have to make some sort of a simplex call. So now you have a situation where simplex is
that's because
absolutely
you represent them as constraints. Now,
yeah,
both. Yeah.
correct, right? So we are ending up having a conjunction of two things, right? So simplex is now absolutely necessary. So this previous way of doing this bound propagation no longer works, right? So what alpha crown can be thought of is, can we still make bound propagation work somehow? Correct? So what alpha crown says that, okay, alpha crown says, you can look at it in two different ways. So the first way of looking at it is alpha crown says that instead of choosing both, what we'll do is that we'll choose a linear combination of these two things. That is to say, we'll choose a line that actually passes through the origin with some slope alpha, right? So we'll choose some line that looks like this. And the slope of this line is called alpha, right? So notice that firstly, you can, alpha is going to be within 0 and 1, of course. And any alpha is sound. So this doesn't affect soundness in any way. No matter what I set my alpha to, it is going to be sound because ReLU is still being lowered about it, right? And then what they suggest is that, okay, now I don't know what my values of alpha should be, but I know that any value is sound. But what I really want is to choose alphas in a way that things are as tight as possible, right? So then this says that they're going to optimize alpha by doing projected gradient descent on alpha, right? So they're going to do the whole bound propagation in terms of alpha. And remember that autolirpa is being differentiable actually allows you to do something like that, where you do a bound propagation in terms of alpha and then do projected gradient descent to optimize the value of alpha to get a better and better bound, right? So this is the idea behind alpha crown. Okay. Any questions?
No.
Okay. So another way of looking at the same algorithm, which is from this LP and dual perspective, is, see, if you want to again do this bound propagation, from this LP dual perspective, all of the upper bounds is fine. So
so this is all for lower bounds that you're illustrating, correct?
yeah, that I'm illustrating. The upper bounds is fine because upper bound is still just a single line, right? So that you can still substitute back in, which means
for
that
for ReLU, this is what it counts.
yeah. So
it's easier.
right, the linear layer is easier, and for ReLU, the upper bound is easier. It's only the lower bound of ReLU which is in difficulty, right? So yeah, so when we're talking about the upper bound, we can just directly substitute it. The bounds, the constraints coming from the linear layers are anyway precise and linear, so we can substitute them. So then propagating those is easy, right? So conversely, if you want to solve this, if you want to actually solve the LP where both of these lines are present, right? Where both this line and this line is present, then it can actually be, done by looking at the dual of this LP. And if you look at the dual of this LP, the coefficient corresponding to the constraint for this upper bound is fine because you can just substitute that as we were doing previously with Crown. So they'll just be 1. And the coefficients corresponding to all the linear bounds will be fine. It's only that the coefficient with respect to this line and this line is an issue, right? So what alpha crown really says is that set the coefficient for this line to alpha and this line to 1 minus alpha, right? So just take, when you're solving this dual by doing some sort of linear combination by taking positive coefficients, just take some alpha and 1 minus alpha and take a linear combination of these two lines. And with that with that combination of these two lines, with that linear combination, you would get sort of this kind of a bound, right? So it is essentially equivalent to taking alpha and 1 minus alpha as the coefficients for these two constraints and then solving the dual of the LP, right? And of course, any value of alpha will still give you a sound solution. It may not be optimal. So then the question is, what do you set alpha and 1 minus alpha to get the optimal thing? One can call an LP solver to find out alpha and 1 minus alpha so that they're optimal, but we don't want to do that because that will be expensive. We don't need it to be perfect. We'll just use PGT to optimize alpha and 1 minus alpha. So essentially what they're doing is they're formulating this dual LP problem, right? So what they're doing is basically, it can be looked at this way. They're formulating a dual LP, formulating an LP, going to the dual, and then solving via PGT. Right? So any questions so far? Because then with this perspective, it becomes very easy to understand what BetaCrown is doing, because this is the necessary perspective to understand why is it the case that BetaCrown is complete. So is this fine with everyone?
Yeah.
Okay. All right. So yeah. So one very minor point. I'll not go into it.
Yeah.
In
So
too much
one quick point, just as a for summarizing. So at the end of the day, the outcome of using alpha crown is still some over approximation across the ReLU.
Yes.
It produces linear and upper bounds,
Yeah.
which are linear expressions, which are
Tighter than Crown.
Tighter than what D poly does, or in the previous case, like you showed, just back substitution.
Right.
Correct.
Right.
Yeah.
Yeah. Yeah. So and it is still incomplete. So this alpha crown as on its own, it's still incomplete. Right. It is only with the addition of the beta crown or with branch and bound that it becomes complete. So how am I doing in terms of time? Not doing great.
Yeah, well, 15 minutes.
Yeah. Okay.
I think you guys can go. But my laptop is here.
No. I don't think that is a good idea, sir. I mean, yeah. I'll try to. Okay. So anyway, so this is just a very very small point. There's an interesting fact that there is mentioned in the alpha crown paper, which is that if you just do LP, alpha crown actually can give you tighter bounds than just doing LP, because the intermediate lower and upper bounds can be optimized by alpha crown. So this is because the intermediate lower and upper bounds are optimized.
So what do you mean by intermediate?
So we had these concrete lower and upper bounds that we had to find to get this LP relaxation, right? So
Those
this,
are like constant bounds, no?
yeah. So remember that we are propagating both the constant bounds and the linear bounds, right? So these
Yes, yeah.
constant bounds can be optimized. So when we're doing an LP, we have to basically achieve the same result by doing LP. You have to optimize each of the constant bounds by making one simplex call, which is very expensive. So what most LP formulations like Planet do is that they do interval propagation to get the constant bounds and then do LP on top of that. Alpha Crown can get a tighter bound than that because it's by doing Alpha Crown, you're also implicitly automatically optimizing these intermediate bounds. Remember, these intermediate bounds will also depend on the alpha. So whenever we are doing this gradient descent, we'll end up optimizing those as well.
Okay.
Yeah.
So I'm going to. I have made a decision. I'll take Uber back, so you can take about 10 more minutes. But in the sense that that doesn't mean that you can take. You have to optimize. Okay.
Yeah. I'll just continue.
and that cannot go beyond like 5 minutes or so. So the shuttle will not. So I'm not going to ask you to exactly stop. With a comma or something at 10 minutes. But keep in mind, this question.
Sure.
So when you mention LP, this LP is still the same. It's still equivalent to deep poly, right?
The LP that it is tighter than.
Yes.
Yeah. It'll be equivalent to deep poly, but Alpha Crown actually ends up doing better than this LP. With the addition of these alpha parameters, because you're implicitly optimizing this L and U at each intermediate point as well.
But
the LP itself is,
yeah. I mean, Alpha Crown is tighter than LP, I understand. But why do you say just doing LP is just? But I thought that doing LP would be better than deep poly, because deep poly doesn't even do LP.
Oh no. Okay. Oh, sorry. I think I misunderstood this. So this LP is the LP in Planet, which is this one, where we're taking both the possible lower bound lines. So does that clarify your question? Sorry for the confusion.
Yeah, but that would be better than DP, no?
That will be better than deep poly.
Yeah. Okay.
So this is the sort of idea. So you have this is the idea. We have deep poly, which is not as great as the LP via triangle, which is what Planet does, which is again not as great as Alpha Crown. Okay, so this is the order of things. Is this okay?
Why is Alpha Crown worse than LP via triangle? Because in LP via triangle, I'm getting a smaller.
No, Alpha Crown is better. I mean, not worse.
So why is it better? Because in LP via triangle, I'm getting a smaller area, right?
Yeah. So this is slightly counterintuitive, but the reason is that LP via triangle, you're getting the smaller area. But so imagine that you have two subsequent neurons, right? So in one neuron, you might be getting a smaller area, but that area itself is also going to be dependent on these concrete bounds, right? So remember that we have these concrete lower and upper bounds. So in the LP via triangle method, these concrete lower and upper bounds are fixed by, in a first pass when we do some sort of interval propagation, right? So if you do that, then the size of, you're removing both of these two things, but you still have this triangle. And the size of this triangle depends on these two bounds. What Alpha Crown will do is that by choosing this line nicely in a previous layer, it will make this bound itself go to somewhere over here. And then, even though you're not taking, the area you're getting is smaller, even it would have been smaller by taking the LP, because the intervals width itself is smaller. The area you end up taking is much smaller than whatever the LP would have taken, right? So in Alpha Crown, what happens is that these lines, these pegs here, they also end up getting optimized implicitly, because these are also some function of alpha. Whereas in the LP method, that is not the case, right? You can make that the case by, if you make a hypothetical LP solver, which will make one LP call for each one of these pegs, but that will be 2 into the number of neurons, that many LP calls you'll have to do, which is probably going to be prohibitively expensive. Does that answer your question?
Yeah. But so in this case, suppose we're trying to approximate this ReLU function, the one you have on the screen.
Yeah.
If we take the lower bound, which keeps 2 but removes 1, doesn't that always give the best lower bound? Like the
So yeah, that will give you the best lower bound for this particular output of the ReLU, right?
right. So if LP just always use that lower bound.
Yeah, but that is locally, right? So it's not very clear. So you can construct examples of this kind where even though if you take this line, you end up getting the best lower bound for this variable. Later on down the line, you end up getting a worse bound because you would have to end up substituting this line somewhere to get the final bound for the output variable, right? And there maybe substituting this line would have been better, or this line would have been better, or some other linear combination would have been better, right?
Right. Okay. Okay. Thank you.
Yeah. So yeah, locally speaking, it's very clear that you should take, you should either take the one that just like you can develop very heuristics, many heuristics. But the point again becomes, what happens globally is really the question, and that is where they are, throwing gradient descent at things and optimizing everything in that way. Okay, so if there are no further questions, then yeah, I'll move on.
Yeah. For the
okay.
PGD, when you say optimize alpha for PG using PGD, what is the optimizer that you use? Function? What do you?
So
You
the
optimize some area or something like that.
no. So the loss function is basically just the lower bound itself. So so the lower bound of the output variable itself. So if I go back, I was talking about in this formulation, there is this, we want to really find the lower bound of x5, right? So they optimize it by trying to basically, they look at the value of x5 that we're getting, and they try to get as large a value of that as possible, right? Because remember that when we're optimizing alpha, what we're really doing is solving the dual problem, which means that we're getting an upper bound for this lower bound, right? And they want to push that as high as possible. So that is what they optimize. So this LB, so what happens is that the LB at x5, so let me just maybe copy this picture here.
I have one question. So doing projected gradient descent is less costly than doing a full out LP.
It turns out to be in this case, yeah, at least according to the experiments. So, I mean, if you do find that surprising, it will be interesting to discuss more. But I think the main reason that is the case is simply because they're going to use things like GPUs and these highly optimized libraries like PyTorch based on GPUs to do the PGD. And I'm not sure if LPs is something that I'm not sure if that is something that can necessarily be parallelized as nicely. And of course, this is all before doing the branching. Once we get to the branch and bound thing, you have multiple branches that will be done parallelly and so on, and they're avoiding any simplex solver call is itself a huge, it's something that you can exploit hugely in terms of optimization or speed. So yes, the point I was making, the other point I was making, that this LB here, this LB then becomes a function of alpha, right? Because we're solving this dual and so on.
Yeah, that's what.
Yeah, and then PGD will maximize this. So PGD maximizes this guy. Right? So it's basically we're trying to get the tightest possible bound, which means the highest possible LB, lowest possible UB, and so on. Okay, so any more questions at this point?
So you optimize alpha at every step when you're approximating a ReLU, or just at the end?
Just at the end. So we do this all by propagation, right? And then the bound that we get at the end is going to be some expression involving, alpha, and there'll be one alpha for each neuron.
So your concrete lower bounds and upper bounds, how do you calculate those?
So those will also be expressions in terms of alpha.
Okay.
So everything is going to be symbolic in terms of alpha and potentially non-linear. So if you fix the lower bounds and upper bounds, then the expressions are linear. Concrete lower bounds and upper bounds in the intermediate states. But if you don't, since those are also expressions in terms of alpha, things can be potentially non-linear, right? But at the end of the day, you're getting a huge expression in terms of alpha. And this is another way in which PGD is beneficial, because PGD doesn't care about this non-linearity. If we were using straight up LP, we would have to make multiple calls to, deal with the non-linearity.
And you'll have like an array of alpha for every ReLU node.
Yeah, essentially.
Okay, thanks.
So one alpha for each ReLU for each intermediate bound, essentially. Yeah. So the paper actually discusses a few different ways of doing this, but this is what they end up doing finally in AlphaBetaCorwn. So that is what I'm talking about right now. This is still not the the AlphaBetaCorwn paper. That is the one after this. So sir, I think I'm doing badly in terms of time. So yeah, let's move on. So any more questions we can maybe take later on at this point.
Yeah. So you can take 10 minutes.
Yeah, I'll try.
Yeah.
Okay, so this slide I'll not really worry about too much, because this is just describing branch and bound, which I've already done. But the point that I want to mention is that what do we need for any branch and bound based method to be sound and complete? So we need that each bound should itself be sound, right? So every time we do a bounding operation, it should be sound. So that ensures soundness. So as long as your bounding operations is sound, you are sound. So that so far so good. AlphaCorwn is going to give us a sound bound, no matter what PGD does, no matter what the value of alpha is. And completeness, for completeness, what we want is eventually we should be able to say something precise about the bounds, right? So eventually we should branch down to some small enough piece where we can get a precise bound, where, if we know that the bound is failing to prove it, we know that actually this can't be proved, right?
This is the refinement process, correct?
Yes, this is the refinement process.
Yeah.
And the general idea is that you branch and bound, and you branch by splitting ReLUs into positive, negative, exactly similar to how ReLUplex would have done. So in fact, ReLUplex is also can be thought of as a, in this sort of ReLU splitting branch and bound kind of thing. So you branch by splitting ReLUs, and then we bound. And how do we bound? We are going to use AlphaCorwn to do this, right? So we bound by doing calling AlphaCorwn, right? So this is the idea. And the key point that I want you to keep track of with this question of soundness and completeness. Sound is because AlphaCorwn is a sound bounding algorithm. Completeness we don't have yet, because even if the bounds are very small, it's not really clear that AlphaCorwn will give us precise bound, right? So that is where the real question comes in, and that is where BetaCorwn comes in, right? Okay, so now let's talk about this a little bit more. So why is this situation not complete? So soundness is fine, right? So we are going to use AlphaCorwn to propagate bounds, and we are going to branch on ReLUs and so on. Soundness is fine, but what happens when we talk about the completeness? See, if you just do back substitution as what we are doing in AlphaCorwn, we will not get completeness, right? Because it is not actually able to detect infeasible ReLU fixes, right? So if we go back to this kind of an example, this is an example that was there in the paper. So if we go back here, so here what happens is, if you do a ReLU split, so suppose you've done multiple branches, and now you're going to do a ReLU split where you're fixing this guy to x1 greater than equal to 0, and you're fixing this to x2 less than equal to 0, right? Now in this situation, if you just do a crown propagation, so maybe when you're doing a crown propagation here, what you'll do is you'll essentially make the concrete bounds of x1 and x2 fixed to greater than 0 and less than 0, right? So when you do a crown propagation, alpha doesn't even if you do AlphaCorwn, alpha doesn't come into the picture, because every ReLU is fixed, and this crown propagation will be precise. But the issue is that this is infeasible, right? This and this can never happen together. And because of that, when you do the crown propagation, at the end, whatever value you have, it's going to be a nonsensical value, and it's going to be, some value that is actually not attainable ever in the network, because you're actually doing a propagation in a case where something is not feasible, right? So this alpha crown paper actually implement a branch and bound procedure, but at the end of the day, they have to do LP calls. They have to do LP calls just to detect this situation where you have done two ReLU fixes on two different neurons, but because of some relations involved in the previous layer, they're actually infeasible. You can't fix this guy to positive and this guy to negative, right? So this infeasibility is actually something that alpha crown on its own can't really take care of, and you'll have to do an LP call at the end. And this paper does some experiments based on this sort of an approach where it will do alpha crown plus branch and bound, and they get good results. Much better performance than existing methods, and it explores more branches. But then this is expected because they're running on the GPU, whereas most of the others they run on the CPU, right? So why is it still you would expect even better method, better sort of results, but you don't get that simply because they're at the end of the day being limited by LP. Their completeness procedure, to ensure completeness, they'll have to do LP in the worst possible situations, right? So then what can we do better, right? So that is where we sort of come into beta crown, right? So before going to beta crown, just for ease of presentation, ignore alpha. And again, as I'm saying, fix the concrete lower and upper bounds. We can go back and talk about what happens to the concrete lower and upper bounds later on. And yeah, so under these two assumptions will work. And the other thing about beta crown is that essentially the idea, the issue with alpha crown that led us to needing to use LP was the fact that we had to propagate these ReLU split constraints, right? When we could not do that, we could not propagate ReLU split constraints, right? So see, alpha crown itself was born out of this sort of situation where we wanted to propagate certain constraints, which is possible via LP. ReLU split it's possible to propagate ReLU split constraints via LP, right? But we were not able to propagate those constraints. So we went to this dual picture and added in these coefficients alpha 1 minus alpha to get rid of that, right? So can we do something similar? And in fact, we can, and that is how you get beta crown, right? So again, let's consider the dual of the LP form. Here, this is the dual of the LP form after adding the ReLU split constraint. So here we have some constraints C1, C2 that are coming from the network. And then some other constraints, R1, R2, so on, that are basically fixing ReLUs, right? And then what do we know? We know that, whatever these constraints are, these can be actually substituted within each other, right? Which means that in the dual view, when we're taking linear combinations, again, the coefficients of these constraints can just be set to 1, right? So we can set the coefficients of all of these constraints to 1, correct? But we don't know anything about the coefficients of these ReLU fixing constraints, right? We don't know any nice way of substituting them back in, which means that we don't a priori know what to set the coefficients of these guys to, right? So what they say is that, okay, let's just leave those coefficients as beta. So they introduce this variable beta, and there'll be as many betas as their ReLU split constraints. And they said, okay, just leave them as beta.
So you don't say what ReLU constraints are? Yeah, but those are the ReLU constraints. When you do the ReLU split, okay, the ReLU constraints are similar to the way that ReLU plex did, right? So
yes.
For the two cases,
there is exactly the same constraint.
Less than or equal to 0. Input is less than 0, and the input is greater than or equal to 0. That's what you mean, correct? So that's
exactly. Precisely that. Exactly the same constraints as ReLU plex. So there's a branch, right? So the branch is ReLU positive, is ReLU active or inactive? And if yes, then we say that, so let's say that x1 is equal to ReLU of x0, or just for notation's sake.
Why couldn't this adding these constraints corresponding to these split of ReLU?
Yeah.
Why couldn't that have been done in the branch and bound method also?
Yeah, they are being done, right? But the question is, when we're adding these ReLU split constraints, this is then, these are some extra constraints that we have to also propagate across the network, right?
Right? Yeah.
And that is leading to the issue. So if we just do a alpha crown or crown propagation, then that will essentially ignore the ReLU split constraints, which will mean that if the ReLU split constraints actually introduces some infeasibility, or if the ReLU split constraints actually tightens the bounds further, we won't be able to detect that, right? So for example, consider this network where we have fixed this ReLU to be active. So this ReLU is, let's say, active, and this guy is inactive. Then we have this situation, right? Where we have this constraint and this constraint. And now alpha crown has no way of handling these two constraints, right? It can handle all of the constraints coming from the network, but these two extra constraints, it doesn't really know what to do with. So, what they do in the first paper is that they'll just ignore and propagate. But then what can happen is the combination of these two constraints might be infeasible, which means that you end up calculating some bounds for situations which are infeasible, leading to some garbage values, which will not be complete, right? So for example, in this network, we can see that x5 is always equal to 0, correct?
Yeah, that's fine. That's fine. So please go ahead and then
Right.
finish up. Yeah.
Yeah. So that is the issue. That we alpha crown can't handle these ReLU constraints.
Explain how that the same constraints are
being
done
handled in the beta crown
here without propagation. Yeah. So
yeah. So in fact, that is basically what I'm doing, right? So previously, what were we doing? If we didn't have any of these constraints, then things were fine because we would have just taken one times this constraint, one times this constraint, and taken linear combinations, or equivalently done back substitution, right? But now we can't do that. So now we have to introduce these parameters beta 1 and beta 2 because we don't know what the coefficients for these two constraints should be, right? So in the dual view, then, we know that the coefficients for all of the constraints coming from the network are just 1. But we have chosen the coefficients for all of the constraints coming from ReLU fixes to be some beta 1s, beta 2s, and so on, right? So now let's come back to the primal view. So now when we come back to the primal view, all of the back substitutions corresponding to the network can be done as exactly as we were doing before because the constraints anyway are 1. But now what we can do is we can substitute these ReLU constraints by multiplying it with some beta 1, beta 2, right? So going back to this sort of example, what we would get is this situation. Okay, so I think it didn't get copied correctly, but anyway. So what we would get is this situation where we have some constraints on this node. There are ReLU fixing constraints, right? So this is x2 is less than or equal to 0. And we also had some constraints involving x2 and x4. So we had maybe, let's say, a constraint, let's say, x4, the original constraint coming from ReLU, which is, let's say, x4 is greater than or equal to x2. And again, we have some constraints relating x0 and x2. So we had x0 is equal to x2 and so on, right? So then what we can do is we can multiply beta with this constraint and add it to all of these things, right? So this basically becomes x2 minus x4 is less than or equal to 0. This will become x0 minus x2 is less than or equal to 0. There will also be another constraint for, the other case, which is the x2 minus x0 is less than or equal to 0. And then you can add beta times this guy here and say that, okay, plus beta times x2. Right? So you add this beta term over here. Similarly, you say again beta 2 times x2 plus these things. So we do the bound propagation exactly as we were doing, but every time we see a fixed ReLU, we add all of the terms corresponding to their constraints multiplied with this new variable beta, right? And that is basically saying that, okay, if we're able to solve the LP that combines all of the bound propagation constraints and ReLU constraints, that essentially is going to be the same as choosing the values of beta, right? So if we choose the value of beta correctly, we can always do that. So now basically, as long as we can choose the value of beta correctly, we'll get a tight bound, okay? Right. So then the idea is again the same. Finally the bound that we're going to get is going to be in terms of this beta, right? And then we're again going to optimize this beta via gradient descent, right? So we're going to try to get tighter and tighter bounds by optimizing beta by doing gradient descent. Okay. Okay. So sort of last slide, I think. Yeah. Yeah. So this is fine. I think we're just going to add back in alpha. So not discuss that in too much detail. But let's talk about soundness and completeness because that is more important. The first thing is that no matter what beta we choose, the substitution that we're doing is valid, right? So we have some expression involving x naught, x1, blah blah blah, less than greater than equal to some 0, and now we have some other expression which is this constraint that fixes my ReLU. So let's say x naught is greater than equal to 0 or minus x naught is greater than equal to 0. No matter what I do, if I multiply it with any beta and add in here, that is not going to introduce any unsoundness, right? It's not actually doing some unsound operation. So it's not actually creating some feasible points where there were none in the LP. So this substitution is always going to be valid, which means no matter what beta I choose, no matter what beta I choose, the resulting bound that I get is going to be sound. So similar to the previous situation, this sort of G beta, this bound is sound no matter whatever beta, right? And similarly, you can add back in alpha and then you get sort of a bound in terms of both alpha and beta, and you can do gradient descent on both. But again, so the similar sort of situation, no matter what alpha or beta you choose, the bound is sound. It's just the case that you not want to choose alpha and beta to optimize the bound as much as possible, right? So that we can do. But now for completeness, right? For completeness, adding this beta actually lets us argue that this algorithm will now be complete without doing any LP calls, right? So notice that when all of the ReLUs is split, the LP formulation becomes precise, right? So now if we can choose a beta that will optimize this LP formulation, we will basically get, we know that the bound that we're going to get is precise. It's going to be precise, right? And the interesting thing is that if the ReLU splits are feasible, right? So if there's no infeasibility, then all of the bound propagation, all of the network constraints directly give you an optimal bound, right? So network constraints, so which are these constraints here, these guys here, they directly give you a precise bound, right? So which means no matter what beta, G beta is going to be the precise, right? In the other situation, else, if the ReLU splits are not feasible, then remember the dual of the LP is unbounded. And what does that mean? That means the G beta in this situation is actually going to be unbounded. And this can be detected. So what you'll see is that when you're doing gradient descent, G beta, remember, is the lower bound, will actually become greater than the upper bound that you have computed at the output, right? So you end up getting some situation in the output where upper bound is actually less than the lower bound, right? So upper bound in terms of beta, I should say, is less than the lower bound in terms of beta. So you end up getting a situation like this. So the dual becomes unbounded, and these two problems sort of, the bounds sort of keep growing and they grow past each other, which is clearly not feasible. And this will basically immediately sort of, stop your search, right? So you found an infeasible sort of domain, subdomain. And this can also be utilized for early stop. So this is what BetaCrown does. And yeah, the experiment section, I think I'll skip because there's no longer any time. Do I even have time for questions? If not, let's take that offline later on. This is all I had.
We have to stop here.
I think yeah, go on.
So certainly, yeah. So I'll see. I need to talk to you guys, okay? I mean, to the two of you, because you're sincerely attending these things as to what you want to do. I mean, if you're really interested in this and knowing more about this thing and so on, we can talk offline about in terms of what you want to do for the presentation, okay? You just because I mean, are you really interested in knowing this? Obviously, this was a rushed presentation because I had put like a gun to the Ganta's head. Okay, But of course, Ankan wants to do something as well. So we have this question of maybe we can discuss this a little later. I mean, basically the question is, if you're sincerely, deeply interested in knowing this, okay, then you could do further reading and then do that as a more detailed presentation, okay, to clarify that out and so on. I mean, I'm going to have like a exercise on you doing using alpha beta concept, but that will be like using them as a black box, okay? But that will be just for in lieu of your final exam or something. I'll give that as a take-home thing. That will not look into understanding, spending more time and so on. So what I'm saying is, you decide based on what you've been assigned. If you've already started reading it, I know that what you're doing is, you say that again? Ah, okay. And what are you assigned? Yeah. Yeah, I think it might be, I don't know. I mean, unless you really want to get deeper into this, it's better that you stick to that. But anyway, think about it. Yeah. Yeah, but present it. This is supposed to be the last lecture, common lecture, if you want to put it. I mean, maybe the October 30th lecture, that Monday lecture on reinforcement learning, that's also at a basic level, because I didn't know how many of you folks had a previous thing. I mean, have you guys taken a course on reinforcement learning? So I wanted to get a quick, because there are two papers that are quite interesting to think. So yes, after that it's all presentations. Yes, but why do you ask that? That is, in class by by Diganta. Yeah, but there is interest, huh? Huh? I'm curious, what is your interest in this? I mean, this guy wants to do research in this area of verification, synthesis, and things. So because that depends. I mean, that also decides on whether you want to go deeper into this or you want to explore a new area. So, what do you think, Diganta? Okay, is it? Because there are lots of questions, okay, here
Right.
that are
unanswered and
was glossed over, okay. And and I think some of that, some of them is what eventually, what is it that happens? Like, for example, in the refinement case, I mean, you say that there is a, does it really converge all the time? Is a question that I still was not able to get answer to here. I mean, is it, when you say it is, so there are those questions. I don't think we can answer you. This is not, it's not going to be precise like reluplex. The result is not like reluplex here, okay? It is only precise to the extent of probably getting some bounds, precise bounds, I guess. Nah? Whereas in reluplex, it is precise in terms of verification in terms of arbitrary predicates and so on. And then but those kinds of things, as when they do some verification, they'll get answer, okay, when they throw the thing. But so the question to you is it do we do other topics like they are assigned? Is it better to know more about those things, or get deeper into understanding what alpha beta crown take? I mean,
So I think that really depends on what one is interested in the sense that if somebody is really interested in, say, making solvers or understanding or any other neural network analysis tool, right? Like a verification engine for neural network or some other tool that can really look into a network from a formal perspective and analyze it. Then in understanding this is really interesting because it is a set of techniques that seems to work really well.
Yeah, that's right. That's if you want to get into the under the hood and then you want to make these techniques better and so on. That is your line of research. Then it is useful to understand. See, I think a common, okay, that is not going to be feasible. I forget your name. Shubhaman? Okay, so giving more lectures for common lecture, that is out of question. Okay. I'm not getting enough people, to listen. Maybe they'll go listen on the thing. But since you guys were here, that's why I'm saying just for your presentation, if there is interest in what you want, both of your bachelors. Yeah. Now, if indeed, then then it becomes relevant. If you're taking just as you want to learn what's going on here and so on, then maybe it is better to stick to your existing assignment, okay? And then do this exercise on verification exercise of AlphaBetaCorwn, which gives you an overall idea of what is the output it produces, and then I'm sure that I will have you do some refinement, okay? And that kind of a thing. And that exercise will be, I'm thinking it'll be a take home, okay? You'll start reading, but it'll be a take home during the, I mean, I'll give it out, okay? But you can do it during your final exam period. Okay, that will be just an assignment that I'll give out and so on. So we don't have to make a decision right now. You can think about it, read the paper that has been assigned to you, and see what you want to do. So for you, I mean, there are two things. One is if you're not interested, doing some project in this area, etc. Even then, whether you want to go get your hand, under the hood of these things, okay, and then go deeper, that will be, it depends on if there is some thing that you want to tweak something in terms of the algorithm that they have developed. Is there scope for that? I mean, I'm not saying Shimon is interested in that, but even for somebody else who might be interested, is there at the master's level kind of a thing? Is there scope for doing something? That's the question for you.
Yeah. I think, I mean, one needs to think a little bit. I think it's definitely true that all of the code base behind AlphaBetaCorwn and AutoLyripy, it's all open source. So there is nothing like no barriers in that sense.
No. I know there is no barriers, open source, and you can do it. But you have to have some problems at hand. Okay.
Yeah. So I think I know that Afzal has recently published a paper working on some different kind of refinement techniques along this line.
I see.
Yeah.
So it's published work?
Yeah. So very recent, this ATVA this year it got in.
Which conference?
ATVA.
ATVA?
Yeah.
Oh, in the upcoming ATVA?
Yeah.
Oh, I see. Okay.
So he's basically taking AlphaBetaCorwn and adding. So this refinement is not counterexample guided, right? So he'll try to.
Lots of questions here. I mean, I didn't even fully understand. I mean, I didn't even believe like what you said about. Why should this be complete? Okay.
Yeah. I think the entire point of this duality was to sort of show that, but I think it was way too rushed for.
That is fine. That's fine. Okay, so I don't think we are getting I mean, I'm just throwing open this question, that's all.
Yeah, sure. And
Yeah,
I'll let you know.
Ankan wants to do something. I mean, let him say. He can.
Yeah, in Betacrown, what I read is like after some time, like they mainly deal with these ReLU splits and they use some Lagrangian multipliers to
Yes,
even
yes.
further converge the bound.
Right. So these betas are exactly the Lagrangian. I mean, so beta times x is exactly the Lagrangian function that they use, multiplier that they use, right?
Yeah, they try to converge it like as much as possible.
Right. But then the question is, so the reason that I was basically debating. So there's a lot of different ways in which one can, I think, or at least two different ways in which one I was thinking of presenting this. One is from the point of view of this Lagrangian multiplier. So to introduce,
Here I'm going to cut it off because it's getting late. Okay, so but Ankan is certainly interested, and I think that we have a solution at hand. Okay, so I think let you guys stick to what what you're doing, because okay, but Ankan wants to do something. He wants to read up. Okay, one of the things that has been assigned to him is that Betacrown paper. Okay.
Oh, okay.
But so then in that context, he could quickly summarize, some of the open things in here.
Okay? Yeah, I think that will be great. And I think, and then some more detailed presentation.
Yeah, so in this presentation, he can make that clear and then add a little bit more.
Okay? Right. So in fact, there is a follow-up paper to Betacrown which extends it to non-ReLU activation. So if it is possible time-wise, both from a preparation and presentation perspective, even that might be interesting.
Well, let's see how it goes. At least,
but at least Betacrown should definitely be covered.
I think that the Betacrown part that was rushed.
Oh, actually, I missed the point that Betacrown was already assigned. Then I would have not even gone into that. I would have just left it AlphaCrown and taken more time with that, maybe. Yeah.
No. I mean, because this is the first time we're doing it, and there is a lot of stuff in here. So
but going over it.
The class is guinea pigs. Okay, so I hope. No, that I was getting to. Okay, so I really don't know. I mean, his is unless. I mean, there's not enough sessions to squeeze everybody in unless we steal some Fridays. Okay, at least a couple of Fridays. Already I've stolen lots of Fridays. And I'm getting raised eyebrows here. As if their holy discourse is how I'm behaving. But that's how it's from my perspective. So I don't know. I mean, what I can do is, that's why Sayanthan's lecture and his lecture, I'm going to make it optional. Okay. So the rest of it, so I've scheduled it on November 27th, which is actually a Monday. Okay. So that I don't know. But Ankan, if you want to do it, you will do it. I mean, I'm not going to insist on the rest of the class to be present, but I think the people who really, maybe they care enough to be present, I'll be there, Diganta will be there, and it's for your experience, and we can do it that way. Huh? Okay. Yeah. So let's do that.
Okay, sure.
Yeah, online, offline is not the issue. Okay. Even if it's offline, if it is during some day, I mean, we can do it offline so they can attend. Whoever is interested can attend. But we'll structure it in such that some of the thing, that was rushed through here could be done a little bit more leisurely. Okay. And, some questions about Alpha Crown can be answered as well. Okay. So let's plan it that way. So those two, Sayanthan's presentation and your presentation will be outside of this thing. Okay. And that's how I plan. But I think there'll be one presentation there. Take a look at the thing, not your presentations, but I think I've scheduled your presentation on a Friday. Okay. And I think that's the only presentation on Friday. Maybe Sulagna's presentation is on Friday, because yeah. So I don't know. I didn't really know how to squeeze this thing because some people kept asking. They didn't want to do. I mean, not that we had time. Okay, they wanted to push. They really want to do later. Okay, because they want more time. So then, where is the later there? Unless I have one full week of presentation. Yeah. Sounds like what? Then you will have to attend every day of the week. No, we can have one day like that, if indeed we want to do it. But okay, so that's fine. Yeah, thank you. Yeah, thank you for showing up and then sticking till the end. So we will decide on the thing, but you will present it. That I've decided. That we have decided. What exactly the content of that will be, and when. Open to when those two will decide. Okay. Oh, you're already scheduled. Oh, okay, so that's good then. Okay, good then. Yeah, so then you guys can decide on that thing. The only thing that I'm adding is, if for the benefit of some people who want to attend, okay, whenever we schedule it, that they, some of the thing that was rushed upon, if there is something that you could recap, yeah, that you could do. Yeah, then you can plan with Diganta on that. Yeah, okay. Is that okay, Diganta?
Yeah, so just to understand, what is it that was decided? I was not able to hear what anyone else was saying other than you and the.
No, I didn't understand your question.
So sorry, I was not able to actually hear anything that was other people were saying except for you. So what is it that was decided?
No, Ankan Kar will be presenting that beta crown paper.
Right.
And in his presentation, we will decide when his presentation will be. Okay.
Right.
So I haven't scheduled his presentation yet because I ran out of slots. Okay.
Yeah.
But we will schedule his presentation.
Mm-hmm.
Right now, I'm saying, since it will be, if it is outside of the term, that's the only way that we can schedule it. That will not be made, it will be made optional for people to attend.
Right.
As far as the content of his presentation is concerned, in addition to doing the thing, if there is interest of a few other people that are now attending to attend.
And we can do beta crown there.
Yes.
That's what yeah. Sure, sir. Yeah.
As part of that is all I'm
saying. Yeah. Sure.
That was the decision. Yeah.
Yeah.
So Ramit and Shobmon will be sticking to their papers. Okay. Reading that. Yeah.
Okay. Sure.
So who are you working with? Now I know that you're assigned with you. So you. Diganta. Oh, okay.
Yeah. So we have been in contact. So we're figuring out some time to meet.
Okay, then he'll stick to the assigned one. No changes there.
Yeah. Sure. Okay.
Okay. Thanks. Yeah.
Bye.
Bye-bye. Go have dinner. Yeah.